She has been here for months at this point, and is coming most recently from Arizona State, where she was an assistant professor before. Also did at least one degree there, and in between, I know, spent some time at Columbia University and worked with some people that some of us are familiar with, maybe particularly Manu Lal, for those of you that know him. I'm not going to say too much about Beth's work. I will let her talk about that today. Beth does a lot with remote sensing, satellite images, applications to flood, risks, people and vulnerable populations, and a lot of really neat stuff. So I'm going to turn it over to you, and thank you for being here.
All right. Thanks so much for having me. I'm going to guess how many people here were at my job talk in February? 3 or 4. There's a little, overlapping content, but really I would say like maybe 30 to 40%. I've actually done some new things since then. The biggest new part that I'll talk about that I thought this would maybe be a good audience for that I didn't do in my job talk was go a little bit deeper into machine learning and some of the newer work with foundation models that my lab is doing. And Sarakash, my postdoc is the foundation model guy, so I will present some of his sort of latest hot off the press stuff, but if people are interested in going kind of deeper into AI and foundation models, then Sarah can help out too if people want to have more discussion about that. It's a very exciting kind of space in remote sensing right now, so I thought this would be a good group to talk about some of that with, especially if some of you are working with any of those or interested in it. A little bit more about me. Kind of before my academic background, the reason I study floods was because I lived in El Salvador for 4 years. I was supposed to be studying fair trade coffee farming. And then the communities I was working with got flooded out. And suddenly coffee wasn't the important thing to talk about. And I ended up staying and starting a nonprofit with community leaders and doing a lot of flood rebuilding and reconstruction. And that has really led to the questions that I work on now and probably for the rest of my life, which is trying to understand how does land change like urbanization and deforestation affect hazard and risks like flooding? What is the role of corruption in government in shaping who gets flooded and who gets access to aid and who doesn't? And why are there informal settlements in these really highly at-risk places? And who's really responsible for shaping where and how cities grow? So those questions really that I lived there is what I'm going to talk about today. I love working outside of academia. I'll talk a little bit about Floodbase, a company that I started about 10 years ago that works in something called parametric insurance, which we'll get into. And then I'll talk about some work that I'm doing with lawyers in environmental justice on the US-Mexico border, but love to do that sort of transdisciplinary work outside academia. My lab is called the Social Pixel Lab because we bring together social science with remote sensing. Most of the work in my lab is focused on flooding, but we do some work on urbanization and deforestation as well, and we're always trying to figure out how are people changing the earth and what is that doing to risk, and how can we use satellite imagery to make people's lives a little better. So that's what we're doing in our lab. And I just wanted to promote new classes I'm teaching since I'm new here. I don't know if we have any undergrads in the room. One is cross-listed with grad, but in case you know students who would be interested in this, I'm teaching an AI for sustainability science this spring. No coding or programming required because I'm going to teach a little bit of it and I'm going to make students do it. I love actually students who are terrified of coding, like getting them unterrified and doing it a little bit because you got to do it if you really want to learn how AI works. The course is mostly based on a report that I was a co-author on that we just released with Google DeepMind, which is Google's like AI lab, and the Stockholm Resilience Institute called AI for a Planet Under Pressure. And we basically review like where are we at in sustainability science with AI right now, what are the main types of algorithms folks are using to solve what problems, and where do we really kind of need to build out a better research agenda in this space. And that's essentially what the class is about, teaching students those architectures and what's going on field. And I'm really excited about this class I'll be teaching next fall, which will be a community-based learning course I got a small grant for. And we're actually going to be working with the organizations I'll tell you about today that are working on flood issues along the US-Mexico border. And this is going to be sort of like an everything you need to know about flooding class. We're going to do hydrology, we'll do the map of return periods and what those mean, a little social science and environmental justice, some economics and insurance, because you have to understand sort of all of those facets from those fields to really wrap your hands around this human environment problem. And we're going to build the foundations of that, and then we're actually going to do a project with a nonprofit who's super excited to work with students to do it. So that's what I'm doing education-wise. So tell folks about those courses. My company that I'll talk about kind of towards the end of the talk has a commercial platform that sells flood monitoring technology, primarily for insurance companies. But sometimes we do event response. We did some actually in the Central Texas floods. We were on the front page of the New York Times because we were really the only technology that was able to make sort of an hourly inundation map of what was happening in Texas at the entire sort of scale of the state at 250-meter resolution. And this is sort of showing. You can see sort of the floodway moving down from Camp Mystic down the Guadalupe River. So I'll talk a little bit more about sort of the technology behind that and some of the commercial applications of this work. So here's the agenda. We're going to talk about AI and satellite data. That's the first part. Then I want to talk about some of my newer work in changing FEMA floodplains and what is the current policy in the U.S. to do that, and some of my hypotheses about why I think that's part of why we have so much growing flood exposure in the U.S. And what's going on with real estate development, both in the U.S. and in Wisconsin. And then I'm going to talk about actually using these data and tools along the U.S.-Mexico border in a project called Flujos, and I'll talk about an insurance application with my company. So that's what we're going to do. But let's start with the satellite data remote sensing part. Many folks in this room probably already know this, but we get more satellites every year. This is sort of the golden age of remote sensing. And I love using this data because we get this really unique picture of where it's flooding from a satellite that you don't always get from a flood model. Turns out it's really hard to predict with a computer where water will flow on the ground. While it is true that mostly water flows downhill, humans have engineered the environment so much that if you don't get the right culvert and pipe size or a tree falling into a stream that moves water one direction, a lot of times it can be hard to predict where water actually ends up going when an event happens. And satellites let us just take a picture of where the water went, and we can map that water on the ground. So that's the primary data source that I use and what I use AI to do. So I'll walk you through some images of this if you haven't seen this before. This is an image from a sensor called PlanetScope. This is a commercial satellite at 3 to 5 meter resolution. This is an image before a flood in South Texas, and this is an image during a flood. It's a little hard to see sort of with the lights, but this sort of dark area here is flooding. This is a drainage canal that's full of water, and there's a lot of kind of dark areas of flooding around that image. And what we're typically doing is trying to extract those inundated areas that you can see in blue with different types of AI algorithms I'll get into in a minute. And this is from an actual event that happened a couple of years ago. And when we compare where it flooded in June 2018 to the FEMA map, we notice a couple of things. One, there ain't none on this side of the image. Hidalgo County has no digitized FEMA flood map. This is actually not that uncommon across the U.S. To update a FEMA map, usually the county has to pay half the cost. So the poorer counties, like the ones on the U.S.-Mexico border, sometimes just don't have it digitized, or it hasn't been updated in 20, 30, 40 years. In Cameron County, where there is a digitized FEMA flood map, it really underpredicts the actual pattern of water because this area of South Texas is rapidly urbanizing. Where water flows has changed. A lot of times, FEMA flood maps don't predict what's called pluvial flooding. So this is like water ponding on the surface, which is a really common kind of cause of flooding in this part of South Texas. So a lot of reasons why the FEMA map might underpredict the actual flood pattern. Let's look at a flood model. Maybe folks have heard of this one from First Street Foundation, or you've seen like a score on Zillow. They actually just took that down yesterday. It was on the front page of the New York Times. Realtors complained that the data was inaccurate, so it's not on Zillow anymore. But this is a commercial flood model that's supposed to be much better than FEMA's. And we still see from the 100-year floodplain of this model just a lot of underprediction of where water actually went in the event. So this is the value of this data. Just you get more here sometimes than you might get from a flood model. And we can use that in different ways. I won't go into depth on like every algorithm my lab's built on, every sensor. This is a table of those things. But the takeaway here is we have to use all these sensors because water moves pretty fast. So you want to use sometimes a radar satellite that can detect water through clouds to capture the flood, or you need lots of different optical ones that are taking pictures at different times and can see different aspects of water. So that's why we have so many different satellites that we use that have different advantages. And we use AI to do this. This is a kind of fun tour of like AI and sustainability science. This comes from the report that we did with Google DeepMind I talked about earlier. And this really mimics sort of what we see in the remote sensing kind of world. And I'll just tell you something about one or two of these acronyms that I think are important. My lab mostly has been using something called convolutional neural networks. That's really popular in remote sensing. There's other sorts of algorithms we've played around with, long short-term memory networks. These have become really big in hydrology, actually, because they're really good at time series data. Really popular for predicting discharge, for example. But more recently, people are starting to move to something called transformers. And this is the architecture behind ChatGPT. One of the issues, though, with transformers is you need like a lot of data to train a transformer network. And so we're starting to see something called foundation models. This is also part of kind of what is happening in large language models. These models that people are building to try to let other people build transformer models, even if they don't have the necessary data to really train that algorithm. So I'm going to go through at least kind of what my lab has been doing with this one, convolutional neural networks, which is really about 10 years old now, and then this kind of newer transformer foundation model world. And that's all I'll kind of do for the AI part. So let's start with convolutional neural networks. Okay, so essentially what is happening in this type of AI is that it's detecting sort of variance in features at different spatial scales using convolutions and sort of this moving window around an image. And you're getting these sort of, at one scale, you know, the curve of an eye or the edge of a nose, these sort of high variance features that then get constructed together into like the actual eye or nose and then the face. This is sort of in medical imaging and sort of computer vision, sort of where convolutional neural networks really became popular. But it turns out it's really great in remote sensing too, because you can extract these features of what water might look like as an object, not just in a delta, but also in an agricultural field, and how that might look different from kind of this larger river system. Water looks really different in different places. And the way you get a convolutional neural network to understand those differences is by labeling lots of data. Like the first 2 or 3 years of my lab was dedicated to painting in water in these images. We have about 700 images of this.
a couple papers we published on it, and this is the data you need to train a really, really good convolutional neural network to teach the computer what water looks like. It's super time intensive, but it does work really well. We've played around with a couple of other things beyond just CNNs or convolutional neural networks, like adding in time series and long short-term memory networks. I talked about this in an earlier slide. That helps. Getting sort of the pattern of a flood wave over time can help you fill in the gaps. And started working with transformers, but really at the end of the day, CNNs are really good. UNets, which is one of the most popular CNN architectures, are great. They still slap. Like, you don't have to get that fancy to make a really good flood map. This works super well, and it's well kind of tried and tested. In remote sensing, we've been using convolutional neural networks, for example, to train a new inundation algorithm for VIIRS, which is a really important satellite. We get about 3 VIIRS images a day, and actually, NOAA's inundation algorithm is run right here in this building. That is, oh, I have it on another slide. But it's not based on machine learning. NASA also has a VIIRS algorithm that wasn't based on machine learning. And they thought, wow, wouldn't it be interesting to see if we can use this machine learning stuff to come up with a better water detection algorithm for this sensor. But instead of hand labeling all these painted images that I showed you in the last image, we thought, let's just use other people's data. So Google produced this data set called Dynamic World 3 or 4 years ago, which makes a prediction of a land class on every single Sentinel-2 image, which we get one about every 3 to 5 days. And we thought, okay, we'll take their water labels, even though they're not 100% correct. Let's use that to train our AI algorithm. We sampled about 90,000 images around the world. This is sort of the target here. And then we tried to mimic it using VIIRS data. Now this dynamic world target is at 10-meter resolution, so much higher than VIIRS, which is 375-meter resolution. So this is like more than an order of magnitude spatial difference, but it still does a really good job capturing kind of these details that we can see in the dynamic world targets. This is the algorithm in this building. This is just one of many examples, and this is the only one kind of I'll show for time. But here is the actual sort of river network from a radar sensor that can detect it through clouds. Here's the VIIRS image for that day. VIIRS is an optical sensor, pretty cloudy, kind of a crappy image, which is why this algorithm is like super gray. This is all no data. We cannot even try to predict water here. NASA also, you can barely see the river network, probably because of this clouds and haze. But with machine learning, it does a pretty good job of guessing what's happening under those clouds, detecting really, really weak signals in the near-infrared spectrum, and being able to actually make a prediction. So we don't have to cloud mask at all when we're using these AI algorithms. The algorithm's pretty good at figuring out what to do with like little snippets of crappy data to reproduce this river network.
Is that the lower Ohio?
I have no idea where this is. This is my PhD students.
Oh, okay.
Students.
Yeah, it looks
learning.
like the Ohio, the Cumberland, and the Kentucky rivers.
I'm gonna have to go find out.
Okay.
It might be. It might be. What we found was that, you know, we're getting these much lower error scores on AI than sort of these traditional algorithms, and hopefully, if NASA, the Lance User Group, approves it in January, this will be the new algorithm that they'll be using every day in their product, which is great. And when you have this better time series data that you can get on inundation that you really need AI to enable, you learn new things about the world that you couldn't have learned before. So for example, we used, this is on the MODIS satellite, this is using CNNs and an LSTM, this kind of time series AI approach to create this kind of 20-year record of flooding every week across the country of Bangladesh. We worked with epidemiologists at Stanford who were able to use that to estimate infant mortality rates from flooding. And their estimates are 45% higher than a previous one that didn't have access to this higher quality data. So you actually get a different answer if you use better flood data. We also recently published a study with economists that were trying to measure the impact of flood-tolerant rice. Like, does it actually work? And at what level of flooding does the seed really start to make a difference? And when is there too much flooding such that the seed doesn't do anything for yields anymore? And they could really only do this because of this kind of coverage and temporal data set. And the important thing is, they were able to really find this window that they could corroborate in field experiments, but really look at data across the country to understand this exact moderate intensity flood where the seed really makes a difference. So this is the applications of some of this new data. So all of that was really cool, but we're scientists, so we're always pushing the next edge of what's cool. Can we do even better? And here's the latest thing my lab is working on. This is a lot of Saurabh's work. It's called geofoundational models. So there's kind of two things that have enabled this, and I'll talk about each of them in turn. One is something called mass autoencoders. So remember when I talked about how painful it was to label all these images? What if we just stopped doing that and just masked out parts of the image and used that to try to rebuild it? Obviously, this reconstructed image doesn't look the same as this nice picture of a bear, but it's starting to get there. And turns out you can do the same thing in satellite imagery. And you can extract these really meaningful features in images, save them as, we call them embeddings, and use that to make a prediction about something else. So even if you don't have any labeled data, you can save a lot of what was used to train these super large models. One of the issues I talked about with these new transformer models was the amount of data you needed to make these networks work. But if you don't have to label, and you can save these embeddings and use other people's pre-trained models, then you too can use a transformer to predict. The claim is almost anything you want about the surface of the Earth. So since we have millions of satellite images and many types of sensors, people have been using techniques similar to this masked autoencoders, where you mask out things in the images, try to reconstruct it, and sort of save the features, the critical features that allowed that reconstruction to happen. That's sort of the intuition behind these. So you can take these really generic foundation models trained on all these images, give them a few of these nice hand-painted labels, or sometimes you can even just click on a point of like, here's in the middle of a forest, and it will recognize, oh, let me find all the other forests for you. And with just a few labels, you can make land cover maps, flood maps, fire maps, soil type, evapotranspiration, gravity. People have really started to extend this beyond obvious remote sensing and like many other types of Earth system processes. So it's a very exciting field in remote sensing right now. And everybody and their mom is now building one of these foundation models. There's like been 50 released just in the past couple of years. So this is kind of the question in remote sensing is like, which one should you use? And is it really worth all the effort to build these? These are sort of the questions that Saurabh is working on right now. So I'll just kind of give one of his key results, and we can talk more in the discussion if people want to go a little bit deeper. In this experiment, we tested Prithvi, talked to at least Paul and maybe some other folks in the room about this. This is the model that IBM and NASA released that they have a grant call out about right now. We tried one called Clay and one called DOFA in this experiment, and we found that, yeah, over like the traditional UNet, the traditional convolutional neural network that we've been using for the past 5 years, we get higher accuracy. And we get higher accuracy on every satellite sensor. Some definitely more than others, but it does seem to be making a difference. But the thing that really matters then this is sort of GT's ground truth. So this is kind of the convolutional neural net over predicting. We don't see that as bad in some of these foundation models, for example. So better results. But the cool thing is, you don't even need that much data to train these models. My favorite experiment that we did was looking at what's called few-shot training, where, okay, what if you just had 2 labels? What's your accuracy? 1 is a perfect score. This is intersection over union, very common AI score. Okay, still pretty bad, like 0.1. 5 labels? Okay. You're starting to get, at least with the clay model, like up to 0.6. 10 labels? You're actually, by the time you have 10 labels, you kind of start to saturate. So that's what's cool about these models. All of this pre-training people are doing in foundation models means in the end, you don't need a lot of labels to get a good result. And that, I think, is the main kind of takeaway from our experiments. But if people want to go deeper, maybe Sarah, you can add more than as well. He's also been doing these same type of experiments to detect glacial lakes and glacial debris and finding pretty similar results, I would say. The last thing for people interested in this stuff is we found, at least in flood mapping, clay is the better foundational model compared to Proofly, but Proofly is so much easier to use. We often sort of recommend for people new to this space, that's kind of the easier one to start going with, and you get pretty competitive results really either way. Okay, so we can use all of this AI to make flood maps. That's kind of the end of that section. Let's talk a little bit more about urbanization and the social science aspect of it now. So one of the earlier studies we did, and this is even before we were using AI algorithms, this is very traditional threshold-based remote sensing on the MODIS sensor, is we made 900 flood maps around the world. Folks have maybe heard John talk about this work if you went to John Sullivan's talk a month or 2 ago. The real interesting insight that we found making those maps was seeing how many people rebuilt in the same place we saw flood just over a 15-year period. Somewhere we estimate, and this is population data is very uncertain, but like 40 to 80 million people rebuilt, moved back in the place that we saw flood. Not everywhere around the world did we see the same pattern. In places like New Orleans after Hurricane Katrina, people left, and we didn't see those places rebuild to the same density. But other cities in the global south, Dhaka, Bangladesh, Guwahati, India, huge resurgence of population in the same places we detected flood. So that sort of brings me to the next question. Why is this happening? Why do we see this trend? And while yes, climate change is increasing to some degree frequency and magnitude of floods, really studies show that it's probably only about 20% of the change in the driver that we see in increased exposure. The real problem is this, where we're building. That's really where we're seeing this increase. Who is affected and who is building there and who has the agency of choice is also another really important social question. There's a lot of structural racism, inequality, deep social reasons why people may end up in a floodplain and may not be choosing to do so, but it might just be the cheapest land where they can afford to live. So that shapes exposure hugely as well. So let's get a little deeper into this urban question, and I'll kind of show you the way that I'm tackling it. Okay, this is a FEMA flood map, and this zone AO, this is the 100-year floodplain. And there's a lot of regulations about what you have to do if you build something in that zone. If you have a mortgage, you have to buy flood insurance. Have to. That's like 60% enforced, so not everybody does it. But you are supposed to, if you want a federally backed mortgage, buy flood insurance. Usually it'll decrease the price of the property. It may decrease people's willingness to live there, and that sort of affects price. And there may be other building permit zoning issues that your local floodplain jurisdiction might not let you do if you try to build something here. So what do real estate developers do? They just change the flood map. So we actually have a policy in the US called Letters of Map Revision that in good faith, if you think where you're building doesn't flood, and you can hire an engineer and show that that's not the case, or that you're going to build something to prevent flooding on that property, like a nice culvert flowing downhill, or a levee or something like that, and you can prove that this property will no longer flood, you can change the flood map. So the flood map, this is in gray here because it's an older FEMA map, gets shrunk down to just this little thin area here, freeing up this land for sort of permit-free development in this area in white. And that's what the company Metro National did. This was a golf course that's in Houston that sold to a real estate company. They actually did this twice. This is a super common practice. They built the subdivision, Meritage Homes, flooded pretty badly in Hurricane Harvey. And actually, there were groups of residents that tried to stop this from happening, did an in-depth study with AGU actually. There's a really cool program at AGU called the Thriving Earth Exchange, where you can go find a volunteer scientist. That's what this community did. And a hydrologist named Steve Emmerman signed up to help them look into this letter of map revision. And what he found was, well, the culvert that they said they would build actually would have gone uphill, so there was no way it would have drained the property. The elevation data was inaccurate, and so there had been some kind of fudging of the numbers on the base flood elevation. And this probably never should have been approved. The civic group tried to take the real estate developer to court, lost, city council members ended up backing the real estate developer, so it was kind of a big issue in this community. But this ended up getting built really with no consequences. And things like this happen all the time. There's been a million changes since 1985 to FEMA flood maps. 86% of them get approved. You can actually go onto an engineering company website, like if you Google, like, get out of my Lomer and engineering company, you'll see tons of websites that'll be like, for $10K, I'll get you out of your Lomer, and people will advertise this as really common sort of real estate development and urbanization practice. And while there may be good reasons for changing the flood map, it could be inaccurate. Some of these are super old and were done very poorly. Maybe some shouldn't have been done. And that's what I'm trying to figure out. How many of these cases that investigative journalists have uncovered do we see across the US? And can we digitize all of that? Well, I tried to ask that question, but the letter I got terminating this grant said, your research no longer effectuates administration priorities. So we rewrote it. Ta-da! Satellite-based evaluation of U.S. flood mitigation infrastructure, and got some of this work refunded. So we are still doing this. We're not supposed to be doing the environmental justice implications of like who gets flooded downstream when these real estate projects happen. Well, we are still digitizing all of these changes and trying to understand, were they justified? When we look at where a flood map got reduced, can we pair it with the satellite image of a real flood event and find out, did this place that engineer said wouldn't flood, did it flood after that? And how many times did that happen? So we just started building out this database, and I can show you at least some of kind of raw time series and maps from it. What we find, for example, is for these letters of map revision, most of them are happening in Texas. This is here in pink. California, Florida, really fast growing and urbanizing places of high population in the US. We threw the Wisconsin line on here so you can see this little purple sliver. Very small compared to urbanization in most states. And I wrote a little bit about this story in The Commons, which is the Nelson Institute's like online magazine. And we call this story the new gerrymander because of all the gerrymandering that had been happening in Texas, and sort of centered it around what happened in Camp Mystic. This is on the cover of the New York Times a couple of days after the Central Texas floods hit in July, because Camp Mystic, they did a LOMA. They did a letter of map amendment. They hired engineers twice to change the floodplain designation so that it sort of narrowly missed. This was the original floodway in red. These were all of these buildings that got moved, if you look at the new maps, that like just very carefully outlines, not along the cabins, and the tragic story about what happened in this campus, 27 girls drowned. So I'm not saying that lomers are like the cause of those deaths per se, but that we do have this sort of under-mapped flood risk that we've allowed to happen and sort of engineered and paid for on our risk maps that I think does cause problems with risk perception that have real human consequences. This is sort of our raw data from Wisconsin. We sort of just pulled this yesterday. There's been 17,000 letters of map change happening everywhere across the state. I mean, you see most of it sort of in urban Milwaukee and suburban areas. This is sort of a zoom in on Madison. These are just the lomers, I think, from last year. And you can see sort of which ones, most of these got approved. This is, I know, in really small text. This one got denied, but I believe all of these others got removed from the floodplain. This is going to be hard to see with the lights. Okay, I'll just skip this. He made this sort of GIF of like every lomer in the greater Madison area over the past 25 years to try to look at some of these development patterns, but now they just look like moving dots. So I'll move right on. Anyway, this is work we really just started over the past couple of months and maybe have some interesting stories about what's been happening in this state with real estate development over the past 25 years. Okay, so that's kind of the part where I'm trying to really understand and look at urban growth and the role of real estate and reshaping floodplain and risk. Well, let's tell some nice stories about adaptation and something we can actually do. And that's what I'll want to talk with. First, I'm going to talk about the work I've been doing commercially in insurance. Why is insurance so important? Because most flood risk isn't insured. In the US, it's very underinsured, and around the world, often not insured at all. And this doesn't just matter for people who are trying to rebuild their homes. This really matters for the public sector, too. There's a lot of loss of yield from farming, business interruption when roads block access to manufacturing facilities or other transportation sites. Hospitals have to cancel elective surgery if people can't get to the hospital. So a lot of economic impact beyond just properties being inundated. And this is what my company focuses on. How can we try to insure those types of losses? And we do it through parametric insurance. So I'm going to sort of walk you through how that works. The idea here is if you have some inundated area that you can see from a satellite, there's some level of inundation, this is like from Bangladesh, that is tolerable or even beneficial for some types of farming. You don't want to pay out in insurance until at least after that point. And then there's some point that there's a harmful flood that it starts to flatten out. That's sort of your limit or exit point. And you can price insurance based on the loss you would expect to get at that amount and the frequency of that flood happening. And that's what parametric insurance does. So instead of someone coming to your house and estimating the damage, it's just a pre-written contract that says when your neighborhood, for example, is 30% flooded, you get X amount of payout. They're usually over very large areas, not individual properties. And that's how this works. And what's great about it is it's just a lot cheaper. When you don't have the middleman doing the transaction costs of the damage estimate, people aren't going to court fighting about the damages, it lowers the cost of purchasing insurance considerably. But you can't just do it based on satellites. We tried, and insurance companies said, no way. Too many gaps in the data. So we had to do something else. And what we ended up doing was taking our satellite observed flood maps and then training the US National Water Model, which produces soil moisture and terrain router. We took stream gauges and rainfall data that's always available. We trained it on the spatial footprint of the flood map using a UNet, this super classic AI method, so that every hour when we get this data from the model, we can make something that looks like this nice flood map. And that worked pretty well. And we published on that in Geophysical Research Letters about a year ago. And that is the data that is sold to insurance companies. That's priced on. I'm going to skip a couple of things for time, but it works a lot better than the National Water Model inundation footprints. That's part of the peer-reviewed work that we have, and people are buying it. So I'll just tell this one story. The city, the first city that bought municipal flood insurance in California, there are 2 that have done it so far. Bloomberg wrote up the story about Fremont, bought this policy that they loved because their previous insurance policy covered this government building on a hill that never flooded. And when floods happened in 2017, of course they didn't get a payout and they couldn't rebuild roads and bridges that were destroyed. But now, because their flood insurance policy is just tied to how much it floods anywhere in their city, they can get a payout, not just from floods that would hit their government building. And they can use the money for whatever they want. So they actually ripped up their existing insurance policy, which rarely happens in insurance. They didn't wait to renew. They were like, screw this, we definitely want this coverage. So we monitor every hour now, and we are like legally obliged, kind of contractually obliged to do this, to figure out when does Fremont get a payout so they can settle that claim. And because we can estimate inundation as far back as the U.S. National Water Model goes to 1979, we can price and do return period estimates from that data. So that's how that insurance instrument is priced. Keep missing these maps. Okay, this would be a map. We're doing this all around the world. Now we're doing insurance for the government of Kazakhstan, every church in Italy, with the Vatican, lots of other cool examples I can talk about. Livestock farmers in Colombia, super flexible to insure almost any type of property or business interruption with this type of insurance. So that's one cool thing you can do with satellite data. But beyond just different types of financial protection, I want to talk a little bit about flood justice. I talked about this in the very beginning of my talk of having sort of a class I'll be teaching in the fall connected to the communities working in this area. But this area in South Texas along the US-Mexico border floods a lot. Most of these are colonias, which are communities that are informally built and not zoned to be in the urban area. But there they are, and they flood all the time because this is former agricultural land, and because they're not incorporated into the city, no one's required to build drainage in that area, so they flood. And when they flooded really badly in 2008 in Hurricane Dolly, and houses tried to file FEMA claims to get some disaster aid, almost all of them got denied, 85%. Households started talking to Lupe. This is a nonprofit founded by Cesar Chavez and Dolores Huerta long ago to support farm workers, but now supports communities in this area. And they started going through FEMA documents and found that FEMA was actually training people to go into homes and try to find out, is the floor damaged because of a flood, or is this just a poor family that doesn't upkeep their house? If you can't tell the difference, write deferred maintenance. And they were systematically training people to do that and denying claims in this area. Lupe took them to court, sued them, and won, which is cool. But it took 10 years for people to then get their payout. And it would be nicer if it wouldn't take that long. So my PhD student, Lucas Valuri, who had been doing his master's work in this area on post-flood survival, started talking to organizations and was like, hey, do you guys think it'd be cool to use satellite data to find out when it floods and then immediately attach that to a FEMA or other aid claim, and could you do something with that data? And they said, yes, definitely. So we did a project. This is an ongoing work. It's called Flujos, Flood Justice Utilizing Satellite Observation, where we build a history of flood maps in that area. And we actually trained it on people's lived experiences of where it flooded. I'll show that in a minute. And it was used actually just this past March for people to direct aid and recovery efforts and do active grant writing around this issue. I was just doing field work there 2 weeks ago that I'll tell a story from before I close. But what we did to get kind of people's lived experiences in the flood map was we printed off our satellite maps, had people draw the errors on our map, like, no, the floodwater goes through here and you missed this big part. Then retrained the algorithm based on where people told us it flooded. This is called human in the loop in AI. And the flood map got a lot better. There's all these places here we underpredicted that after we retrained with the new algorithm, we were mapping a lot more water where people told us it had flooded. So that really helped. And I was just there 2 weeks ago, and I'll sort of end with this story. We were walking around this colonia called La Piñata, and people were telling us about how badly it flooded just this past March. This is a irrigation drainage canal, so you can kind of see like why this floods, this sort of legacy of sort of colonization in this area and all this built agricultural infrastructure that is flooding people now today. They were like, yeah, it flooded really bad in March, and people were showing us high water marks on their houses, like people's roofs sort of had molded out, really, really bad flooding in this community, and talked about hearing like the water coming out of the canal and flooding this area. But they said, you know what's weird is it hasn't flooded here before. We were like, really? Let's go check the data. So we looked at previous maps and big floods that had happened in 2018, 2019, 2020, and people's stories really corroborated what we saw in the satellite imagery was it didn't flood in 2018, but it did this time. So this is sort of leading to these new questions of like, what happened? Why did this flood? Is it the urbanization dynamics of this area? There was a widening of the canal further north of this community. Is there drainage sort of being shunted into that area? So now we're working with community-based organizations who are trying to confront the drainage district about this issue. And this is sort of how we're using satellite data to then, help communities build sort of their advocacy to think about how to solve this engineer problem. And I think that's where I'm going to end. So we talked a little bit about AI and satellite data to map flooding and exposure, what's really shaping urbanization, what's happening with real estate developers changing flood maps. I don't know yet, but I'll know maybe in a year. And how we can use satellite data to adapt, to build new types of insurance products, or to work with communities who are advocating for their own change in flood mitigation efforts. That's it.
Great. Thank you so much, Beth. You've given us a lot to think about. We do have some time for questions. I have lots, but I'm going to defer to others if they have some questions first. You explained everything perfectly well, I think.
Yeah.
I was thinking for the parametric insurance, like obviously parametric insurance is itself kind of an adaptation. You get a payout that you wouldn't have otherwise. But one reason economists like parametric insurance is that it kind of alleviates this moral hazard kind of problem. So like in crop insurance, it's been pointed out that you have this incentive to not really adapt to climate change if you have crop insurance, because you'll get a payout and you have to suffer a loss. The parametric insurance, it's not tied to the loss, it's tied to the weather, basically.
Yeah.
So that's made me think, do people, in addition to like getting this payout, do they adopt other kinds of like adaptations? Like you get a kind of double adaptation benefit because you can both like not suffer the loss and get the payout anyway. Have you seen anything like that, or like, even like anecdotal evidence of like they invest in like another adaptation as well because they have this parametric?
Yeah. I don't have anecdotal stories from it, but I've heard economists talk about this, but I don't know of any studies that have formally tested it. Flood parametric insurance is super new, like just past couple of years. Bangladesh had some kind of early pilots in 2020, but drought parametric insurance has been around for much longer. And so that would be the place I would go to look that maybe would have some of those stories, because yeah, if you adapt, you get the payout anyway. So there is a pretty big incentive to adapt and still enroll in double, you know. But I don't know. I don't have any real stories of that happening. Yeah.
I can talk more about
Yeah.
that later.
Yeah, I mean, so the satellite record goes back about 40 years.
Yeah.
And the best satellite probably goes back to 20 years, so there's
Yeah.
a 20-year history.
Yes.
So are you underestimating exposure?
Yes.
Okay.
Yes.
Next
I mean, all we can do in sort of satellite-based exposure estimates is see like where did it flood pretty recently in the past 20 years. We can't estimate very well the like the 100-year, the 500-year return period for that reason. Although those statistics are maybe somewhat meaningless, but yeah. So using the national water model, we can at least get a 40-year estimate. That's better than 20. The thing with parametric insurance is it actually sort of hits this sweet spot. We got a better upside on this. We did do a comparison once with Fathom, which is the company that built the data for First Street Foundation, of like, looking at satellite data and flood models in the same location. And what we sort of found was like exactly what you would expect. The sort of more frequent flooding, 10, 20-year return periods, the satellite data typically did a better job. And as you get to the 50 or 100-year, like anybody's guess, and once you're beyond that, yeah, probably you should just be using a flood model. So that's a somewhat obvious outcome. But parametric insurance often pays out at these lower return periods. They can sometimes be at the 10, 20, 30 years. So that ends up sort of being okay from pricing from an insurance standpoint. What you can't use it for is like the super tail events, 500,000-year events, catastrophe bonds are kind of a common parametric type instrument for those. Hard to use satellite data for something like that, but we're trying to figure out some way to do it with stochastic modeling, and we're sort of working on that problem, but yeah, definitely only tells you really the recent history.
Hey Beth, thanks so much for your talk. I actually have a question from a friend who's watching for me. And he says, what is the role of small local adaptations in urban areas like biosoils or permeable surfaces and those foundation models? As more and more of these green infrastructure type practices are implemented, what would it require, or would it require a retraining? Did that make sense? I can also repeat.
Yeah.
Yes. What is the role of small local scale adaptations in urban areas like biosoils or permeable surfaces and these foundation models? As more and more of these green infrastructure type practices are implemented, would it require a retraining?
So yeah, I'll answer, and I don't know, Sarv, if you understood the question, if you have thoughts about this too. So hopefully not. Like ideally, if you've trained on enough of that distribution, like if you've trained on a lot of cities that have bioswales around the world, theoretically, if my new city, A, that recently built a bioswale, and there's a satellite image and a flood that happened, and I apply my model that's been trained on all of these other cities with lots of bioswales, it should be able to figure out sort of the relationship between bioswale and the elevation and what it's seeing in the image and where it's seeing water, et cetera, and figure out some of those relationships theoretically, if the foundation model has seen a lot of that type of variance. But something as specific as a bioswale, like I don't know any foundation models that sample, on anything more specific than just like, I don't know, land cover type. Like you'd have to do some, I don't know, if you have some really custom fine tuning.
It just look at the appearance of feature and try to find out the spatial relationship and the local information it has. So yeah, it doesn't go very specific into the soil type unless you are using some domain specific foundation models which are coming out. Like there is one land segmental which mostly about like land use land cover type. So those maybe go more deeper into the soil type, but not this one that we have used so far.
And also, I think depends like what you're trying to get out of the image. Like if you're trying to map other bioswales, like I don't know if a foundation model has seen lots of things that look like that, it might work. If it's just water, like, the bioswale doesn't matter. Like, if you're just extracting water from the image, ideally you should be able to do that regardless.
Time for another question or two, if there are any? I'll maybe ask one then. Thanks, that was a great talk. So, thinking about the newer AI Earth observation models, you were talking about foundation models and the ability to use less and less labeled data. So when you use less, and I don't know anything about these, but if you use less and less labeled data, are you really able to identify something? Or are you really just looking at, this is different than something else, and I can identify all these things that are the same, right? So is it saying water, is it saying forest, is it saying this? Or water and forest, I'm trying to make it simple for myself,
Yeah.
are different, and it's just labeling things that are different. I mean, at some point, there has to be some labeling, right, for it to know what it is, and then it goes and it learns that eventually, right? If it's
Well-
completely unlabeled,
Yeah, let me give a response from the start if you want to piggyback on this too. So the idea is that in these pre-trained foundation models, you just think of it as like a general model with these really general features, and that's what embeddings are. And you could think about like if you're saying like clicking on 3 forests and 3 lakes or whatever, it's gonna try to extract the embeddings that are most differentiating. What am I say about this? No, maybe I don't. Most differentiates those 2 things from each other and then maps the rest of those things. But it's not just, I mean, so it is doing it based on the difference of those 2 classes, for example, but it's doing it based on like the embeddings that are related to it. So if you think about like just like principal component analysis or something, think about it like that. Like it's trying to find some recombined feature that is giving maximum separability between those 2 things. Or you can do, I mean, people have shown though that you can do like 25 different types of crops and still get really amazing separability. So, I don't know, sorry, if you want to add to that.
Almost correct. Like here, we do need some labels initially, and it depends on the application if they are going regional to global. But at the same time, they have potential for like, which is called zero-shot experimentation. If you don't have any label, you can try it, but it depends on the how complex the problem is.
yeah.
But it has capability of going like zero-shot without even a single label.
Great. One more question?
Yes. I'm curious about the geocondition model you mentioned. I'm curious about the possibility of like fine-tuning that model to like a reasoning flood indentation model, like user just input geographical coordinates and the model can tell them like what is the flood risk, what is the area of the indentation. So is that possible using that geocondition model?
I don't know anyone that's done this yet, but I don't know, Sarah, if you want to comment on sort of like what people are starting to bring together, sort of like satellite and kind of vision-based geofoundation models with language-based models, and having some success doing that. I don't know of anyone that's done that for flooding specifically, but
Like we did it exactly
for
for
the
the
glacier
glacier
one.
lakes. So yeah, so it is possible. Like in this experiment, we are mostly fine-tuning the models, but yeah, now the domain is shifting toward like combining vision and language-based model and giving more as an input, not just the pixel-based label, but associated text, and getting the output not just as a segmentation mask, but yeah, the scene description, like how much is flooded or where is it flooded. So this is very forefront, and like this very recent paper for like DOFA plate. So we have like people are working on it. It's very super recent. I think in the next top leading AI conferences, we're gonna see some of the people, because most of them are in archive, but that's my assumption that there are some people.
Alpha Earth, Google's sort of embeddings model too. They ingested Wikipedia, and part of their embeddings are related to sort of text. So that it's definitely